Alright, let's have a quick class today. I have something I need to attend to.
Me too. Me too. I
I'll send you the details. Oh, by the way, we'll have an exam today, okay? I have sent you an email.
So it's like an exam.
It's an extra credit thing.
It's just like MATLAB, like the maths, or we just need to write, like, you write down in the paper, or you just
No, do it in MATLAB.
You're gonna get a problem like on
Right,
our
right.
labs.
Think about the labs. Whatever you have been doing in the labs, you're going to do that.
Will we be able to use resources?
Hmm?
Will we be able to use like resources?
No, you cannot.
No, so this is straight utility.
Yeah.
So be it. Let's play.
Alright, last class what we did was we discussed we started discussing second order systems, right?
I wish I didn't have to dissolve your fly.
So last class what we did was we defined second order system as, again just to refresh your mind, order of system is equal to, right? Tiffany? So you guys, always, you're always involved.
Right now, I'm looking for a pencil.
Come sit here.
Oh,
Order of system is equal to order of polynomial in the denominator of transfer function. Okay? So this we have established. So second order system by that definition would be the order of polynomial in the denominator would be 2. Okay? Now we also discussed how do we categorize or second order systems. We identified 4 types of second order systems. Correct? If you remember, and it is purely based on this roots of the polynomial. So when we categorize, we said roots of polynomial, right? Real and distinct is what? Over time. Complex is underdamped. Imaginary is undamped. And then the last is real and repeated. It's critically damped. This is what we, okay. Again, these are the only options you can have for a second order systems, right? These are the only routes you can have for second order systems. So you can categorize the systems by that.
That says real and what?
Repeat.
No, not that one.
Distinct.
Distinct.
Now let's look at the general. We introduce something called, and for all these types of systems, we have also looked at the responses. If you just go back and look into your notes. Overdamped is response is very slow. Underdamped, you will have oscillations. Undamped, infinite oscillations. It will always have oscillations. Oscillations never go away. The difference between these two is this is marginally stable, this is stable. Critically damped is kind of the perfect system you desire. This is your system. It will have the best performance and the best characteristics. It's somewhere between these two, overdamped and now the general second order system we introduce something called, every system will have a natural frequency. Okay. We use the symbol omega n for that. This is frequency of oscillation without the damping. Okay. And then we introduce other terms for coefficient. We use this symbol zeta. This is called zeta. So this zeta is defined as exponential decay frequency and that divided by natural. This is simply 1 over 2 pi into natural period over exponential. Period over
Are we multiplying by the natural period or as multiplying constant?
divided by.
Well, no, I'm saying like, is that equal to?
So yeah, this is equal to zeta is equal to this or it's equal to this.
Oh, I'm saying this side is that multiplied. Is
Yes,
Of
it's
course.
1/2 pi times.
Times the natural period of.
Mm.
So now think about, recall this. Recall. What is it? The general notation we used was b square minus over a square plus as plus b. Now from this, can you tell me what would a how would a system oscillate without damping? How would the system look if it oscillated without any damping? What system would that be?
That would be, the
If the
imaginary.
roots,
Huh?
if the roots are real or distinct or complex, unknown.
The isolation would never go away.
No, what if they? I'm asking you, what would the representation be if the system, or what category would the system fall into if the system did not have any damping?
Imaginary.
Huh?
Imaginary.
Now,
Imagine undamped. It is in there. Undamped, not damped. Right? So what would that mean? This would mean this system would look. What would the system look like? B over an undamped system B over S square plus B. Right? So if you look at this, what are the roots of this system? Roots are
minus, I, B,
plus or minus
plus minus
Bj or JB
I,
or dual complex. So this would be that system.
What
Okay.
was that question you originally asked everybody?
For a system to oscillate with natural frequency, there should be zero damping. When, for which of the system is the damping zero?
That's what you were saying, the undamped system?
Yeah, undamped, what does it mean? What do you understand by undamped? What does the English meaning of undamped mean to you?
It doesn't decrease.
Undamped, undo, no damping. Un is what? Un is what? No. Right? Undamped is no damping. That's simple. Right? This one does not. This has damping. This has damping. Although it is less. This has damping. What does this have? Don't have. It doesn't have any damping. That's the reason it is called undamped. Right? If you look at undamped system, this is how it will look like, because the poles are here. The poles are purely imaginary. Okay. So here, see, omega n here is simply equal to root of b. Okay. You have to understand what this, again go back to the response. What would be the, if you go back to response, pole determines that how it responds, right?
It'll be I or J.
Right. So omega n, we say on this, we say omega n, which is the natural frequency, is equal to plus or minus j root. Okay. Or omega n square is equal to. Okay?
Omega n square is equal to minus.
Omega n square is equal to minus 2. Similarly, I'll just write it here. We define zeta as equal to, or A is equal to zeta omega. Think about it. B is equal to omega n square, and A is equal to zeta omega n. Okay.
The A and B is coming from that GS number.
Hmm?
The GS. That's where the A and B is coming from.
Right. Yeah.
That's the square root.
So if you have to, what did I do here? I just showed you that for an undamped system, this is, so here this pole is equal to the natural frequency. Okay. So if you do some similar assumptions, or if you work out in a similar way, you will get A is equal to 2 zeta omega n. Okay.
That's the same.
What's
Why
up?
is it J instead of I? Why is it J? The J, why is
J is actually, this is plus B itself. So this is, we use J here. The textbook uses J. It's I only.
But that is the
It's
imaginary
I.
number.
That is the imaginary. Yes, I is the imaginary symbol.
But it was still
So B is actually omega n square. It's not minus. It's omega n square.
What is the on top of the A equals?
Huh?
You know? What is that on top of the symbol you got there?
And similarly, this is A. From A, you can write G of S is equal to omega n square divided by S square plus 2 zeta omega n S. See, this was, now compare, here what you need to understand is, these two are comparable. Okay, this is written just in terms of polynomials, some B, some A. Okay. What you see here is, it's written, it's expressed completely in terms of the system's natural frequency and the damping ratio, or the damping coefficient. So if you know, we can experimentally determine any system's natural frequency or the damping ratio. Yes.
So those equations you gave are for undamped system only, this is for a general period.
General. This is a general. This is a general. So what I here, even if you don't understand this part, that's okay. Here I just derived this omega n. Why omega n square is B. Okay. You can look at the same thing and derive an expression for this this A, as 2 zeta omega n. And if you substitute that here, so you have B is omega n square, A is 2 zeta omega n, 2 zeta omega n, S remains as it is, plus omega n square. Okay. So here if you compare, what you're going to see is, if you have a second order system, right? Think about that, the 2 mass spring damper system for a minute. When would that be a second order system? When you have one mass, it will be a second order system, right? Now, think about that thing is boxed, it's black boxed. All you can do is, you can provide an input and measure the output. Alright? Can you determine what is the system parameters, or can you build that system? Can you build the transfer function of that system just based on the input output? You don't know what is inside. Okay? So it's like, you're given, this is the system. This is the output. This is the input. What is here you don't know. All you know, this is a second order system. You don't know how many springs are there, how many dampers are there. Okay? You know this is a second order system. Can you determine C of S over R of S? C of S over R of S would always be omega n square divided by S square plus 2 zeta omega n S plus omega n square.
Always.
Huh?
Always.
If it's a second order system, it will always be like this. It may have a gain, but overall the system transfer function will look like this. So just by, if you look at the output, can you determine the frequency of that? Frequency of, if you look at the output of the system, can you determine the frequency? Huh? Can you determine that? So you substitute that here. Can you determine the damping coefficient of that system?
From the output? From the output?
You can determine the output, the damping
If it's
coefficient.
like plus something, if it's like the natural frequency plus.
So what you can do is, you can subject this to natural oscillations and then damped oscillations. We'll do that. But if you do that, all you have to do is determine this natural frequency, determine this damping coefficient, and you have the transfer function. Without going through any math, any physical modeling, what you have done is, you have figured out what the transfer function of that system is. You understand what you have done?
How do you determine the damping coefficient?
And I'll tell you how to do it. But experimentally, you can determine the damping coefficient of any system.
Aren't there formulas for that? Like the formulas we use in stability and control? Would it be
What
the-
formula?
I can't remember off the top, but I think it was like one minus something. It was like something.
Formula, I just gave you the formula here.
To say that they.
Exponential decay of frequency and natural frequency. Okay? This is the formula.
Okay. It's something else I'm thinking about. I'll bring it to
Thinking
you.
about something else.
Yeah.
So this is a very easy way of, this is a very alternate way. If you want to, there are a lot of times you will encounter black box systems where you don't know what is inside. You just by looking at the response, you can figure out what type of system that is, and then figure out pretty closely what the transfer function is of that system is.
Is that what the black box in the airplane does? It records all those oscillations and stuff.
That I think is different. I think it's more of.
I just heard you say black box.
So black box means something you don't know, right? This is a non-destructive way of figuring out the transfer function, right? What is a destructive way? You'll open the black box, you'll figure out what components are there, you'll try to model each component, right? You don't have to do that all the time. If you subject that black box to some kind of input, known input, and you can measure the output, you can figure out what that transfer function is, which will help you model that system. Okay. So we'll stop here.